Hello, everyone. I hope everyone is doing well. Today is Friday, October 23rd. It's 12 noon in South Carolina. And today we've been going all over the world recently. Last week, we were live from Turkey, and we came back. We're coming back home, and we're chatting today with Professor Laine Mears from Clemson University. Laine, how are you doing?
I'm doing wonderfully. I'm glad you pointed out it's Friday, and I'm here in the lab up at CU ICAR, and really looking forward to this. I'd like to thank you for taking the time and the service to provide these kinds of webinars. I know that's not an easy effort, and so I really appreciate it.
Thank you so much, Laine. And I'm excited that I'm hosting you for several reasons. Of course, we start with the professional ones. I mean, you're someone I look up to, your career track so far, and we're going to be talking about that. But also the recent interaction we've been having and working on recent joint work. So that's something very, very exciting. I want to say to everyone who just logged in, and if you're hear us, go ahead, throw in the chat, hello, where you're from, which country you're joining us
from. Great idea.
Yeah, just to start this chat together. And Laine, I'm going to just show people a little bit in the background what's going on. So this is a little bit, we are once again live from Clemson University with Professor Laine Mears, and this is CU ICAR, and you're going to talk to us a little bit about what we're seeing, what is the experiment, what is the research, and all of these things shortly. Cool. So let's go ahead and get started while people are saying hi to us, introducing yourself, and talking about a little bit your career track. So go ahead, introduce yourself to us.
Yeah, so sure. Thank you very much, Ramy. Thanks for the opportunity. So I'm Laine Mears. I'm wearing my mask today. I got my ears covered up because I'm here with my colleagues in the lab. I'm really a really good-looking guy, so just take my word. I understand that. So I've been at Clemson just short of 15 years now, and before that, I spent about 10 years in industry. So I was in the automotive industry as a Tier 2 bearing manufacturer, and then with a Tier 1 automotive drivetrain parts manufacturing. And then I got to escape, and I got to go do my PhD down at Georgia Tech. And then I got this opportunity to come in here and help start up, not just, we're looking at the assembly center, and I'll talk about that, but not just this area, but actually the whole CU ICAR, which is the Clemson University International Center for Automotive Research campus, which we're a campus in Greenville that's off the I-85 track. I'm looking out the window, I can see I-85 right here. And we're away from the main campus about 45 minutes. And we kind of came in, and this was 2003, 4, 5, and then I came in 2006 as part of the manufacturing group to help develop a program of research and education that will benefit the automotive industry specifically. The whole thing started with Clemson University leadership and automotive company OEM leadership discussing, of all things, a wind tunnel. And Clemson said, hey, we got some money. We have some land. What if we built you a wind tunnel and we could get some real research going with that? And the response was basically, we've got plenty of wind tunnels. What we need is a pipeline of good talent that really understands automotive design, automotive manufacturing, and how the integration of different types of systems affect one another in the automotive industry. And this was really a missing piece that Clemson stepped up and filled in. And I was part of that core team. It was a lot of work. And now it's really nice to look back on. We've been successful. Our students go out and make a big splash in the automotive industry. We have folks at Ford, BMW, companies overseas. Honda is really big. Tesla, a lot of the startups that are coming in and now competing with Tesla. And so our network is growing and growing. And this is just as the program was designed. And I'm really, really glad to be a part of it. My own personal research, I'm the BMW chaired professor in automotive manufacturing. So I sort of lead the manufacturing efforts. Not to say that I direct everything, but I kind of pull everybody together in the automotive engineering department and kind of set some directions for how we want to go and some visions for how we want to do automotive manufacturing in the future. And that's really what we're doing here. So we are in the Clemson Vehicle Assembly Center. This was established 2 years ago as a playground for assembly, and I'll tell you a little bit more about that. It's kind of a factory that makes cars, but if we break things or we shut it down, nobody's coming out and screaming at us. So it gives us a kind of a safe place to come in and have fun and try things that you probably wouldn't try otherwise.
The ability to fail and learn from failure.
Oh boy, it's so important. It is so important.
So I mean, Laine, you're being a bit modest. If I look a little bit, you have a career award, the Ralph Teeter Educational Award, the SC Governors Award, and all of these things. So that's really awesome. I'm honored.
Yeah, but that's not Laine. That's Laine's team that he put together. Each one of those things is as a result of collaborations that I've had, of team members that I've had. So nothing happens, as you know, Ramy, in academia and actually in life. nothing good happens without a good team behind you. So I definitely want to make that point clear.
This is the attitude that I have. I always like what you just said is, and if people you're listening to us right now is, once you start believing in working in a team or in a group, and this week I just posted something about this on my LinkedIn that had a lot of interaction, and I was talking about how sometimes for the sake of team you have to compliment people. You have to go and say, you did a good job here. It's good, and very often we miss that. So
yep,
that's very important.
Yeah, you can never do that. You can never do that enough. And I fall short myself on it sometimes. Where you're always looking, as a visionary kind of person, which I try to be. You're always looking at, okay, that was great. What's the next thing? And so keep on pushing everybody and challenging people to move forward to the next thing. And sometimes we forget to sort of celebrate the small victories along the way. But
I agree with you. So I have a question for you. So it's very, very interesting, your chart. I mean, you have academia, you have industry.
Yeah.
And at the end of your undergrad education in 1993, you went to industry. And then
totally.
You went back to academia, and then you went back to industry, and then you came back to academia.
Yeah, that's right.
So which one you like more? Is it a tough question to ask?
No, it's not a tough question. I like academia more, and the reason is on the industrial side there are plenty of good lessons to learn, and I learned a lot of lessons in industry. There is no classroom that you can sit in that will give you the kind of gut understanding of what manufacturing is all about unless you go and spend some years in the factory. And so that's what I did. I didn't do it by design. I didn't say, oh, okay, I'm going to grow up and be a professor one day, but I'm going to need to go out and work for 10 years to really understand what that means. When I finished my undergraduate degree, I ignorantly got in line with everybody else at the career fair, and went around and talked to companies and found something that sounded interesting, making ball bearings. Well, that sounded interesting to me. I was kind of nerdy, but yeah, go make ball bearings, and I was going to go do that for 30 years and retire and buy a beach house and go have fun with the kids. That was sort of my life plan at that time. And then so this was in Georgia, and one day I got a postcard in the mail that said, "Hey, while you're working, why don't you go ahead and get a master's degree?" And I was like, "Geez, that's going to take some years of effort. I'm going to be like 30 years old, when I get done with that." My next thought was, well, I'm going to be 30 years old anyway, and this sounds interesting. And so I jumped in and did it. That was the beginning of the distance learning and professional engineering program at Georgia Tech. And I didn't know it at the time. Georgia Tech turned out to be a pretty good school. I was happy about that. But if some other university had sent me a postcard, I might have ended up there. So yeah, so these little doors of opportunity open, and you walk through them. And that's why you see me coming back to this master's degree at Georgia Tech. I was working full time, so I was just doing sort of one class at a time. That's why a master's degree took me 4 years. And then I got done with that, and I had transitioned jobs right at that time. So between SKF, which was a great company to work for and is still doing very well, into Hitachi Automotive Products. So I wanted to learn about other processes besides machining and heat treat and the things that go on with bearings. And so I got done with my master's degree and got a little round of applause at the company meeting, right, which was fun. And then I was like, now what? I really liked that. I really enjoyed thinking like that and solving those problems. And so I worked for a few more years, took a few more classes, and then jumped out and went full time. Got hooked up with a wonderful advisor at Georgia Tech, and we worked through a very interesting applied research problem. And I knew I was on the right track at that time, and then got the opportunity to be here at Clemson.
This is awesome. So for folks online, any question you have at any time for Laine to profit from the experience, go ahead and post it, and I will make sure to share it with Laine.
Yeah, if you could take that duty and sort of whatever questions look interesting and filter those out, I'd be happy to answer anything.
Absolutely. So talk to us a little bit about Clemson University.
Clemson is great. Clemson is like the little brother of big research universities. We just made 2 years ago what's called the Carnegie. It used to be called the R1 status. Now it's like the highest research output kind of university. So we're a real research university now at the levels of funding. And the whole time I've been here, things like ICAR were big investments that Clemson had the vision to say, we got a great opportunity here and we're going to move forward with this. We don't know if it's going to work or not. We're starting a whole campus and a whole department around the automotive industry. It's the Department of Automotive Engineering. Nobody's ever done this before. We built this department up of graduate students, masters and PhD students from nothing. And we started out with 15 students, I think. And now we're, pre-COVID, we were up over 200. We're of course a little down now, but we expect that to come back. And so those kinds of investments and those kinds of risks have paid off very well for Clemson. And I've been really pleased to be working here. The administration has supported me in everything that I've done from the time I was a little junior guy, or I had to start my career over basically. So even when I was a little junior guy, I got everything that I needed. And again, that kind of support has made me very successful. We like to say we're the technical university and the high-tech university of South Carolina. But I'll forgo that because I'm working with my friend Ramy here, who also has actually a pretty good technical department down there at USC.
Bring it on, Laine. I'm ready for it. I honestly find it a little bit, sometimes rivalry is fun and rivalry is interesting, and actually it helps all parties get better. I mean, this goes without saying. But for me, I believe there is so much work that is needed in South Carolina on the level of education that I think we need four more USCs and Clemsons in
Yeah,
order
sure.
to meet what is needed. So
I'm telling you, the need is so great. South Carolina, I really enjoy because they've diversified the business as tourism at the coast and medical and aerospace and manufacturing, sort of high-tech manufacturing that was originally rooted in the textile industry and now has branched into all kinds of things, not the least of which is a huge automotive company. So now BMW came here in 1992. Volvo has now started up their plant as of 3 years ago. And so we have two major OEMs here in the state. And I agree with you, Ramy. We need a lot more researchers in manufacturing. We need a lot more researchers in transportation and some of the supporting systems that go along with this.
by the way, questions are flocking in, and I just
throw some in as they make sense if you want to do
yeah. I mean, I before I start, like, let's wrap up this first portion where you're introducing the college and you've introduced Clemson, and we're gonna jump into the research. But before that, two things I want to tell you. The first thing is we've received messages from folks, hello, from all over the world, from the United States to Brazil to Paris to Iran to Lebanon, all over the world, Austria. So,
fantastic.
so we have a pretty cool community that is
great. Merci, danke, obrigado.
So, wir können im Deutsch sprechen. You know,
Ja.
with me because
Ja, wenn wir müssen.
Yes, sehr gut. So let's go ahead and start talking about CU ICAR. So what is CU ICAR?
Yeah, so ICAR is actually the campus here. So we're 250 acres. We comprise 5 neighborhoods, one of which is completely built out, and we're getting ready to break ground on the next one. So this is another long-term plan that Clemson has put together to say, we have these neighborhoods. So the neighborhood will have a Clemson anchor building, and you can see it sort of off to the left in this picture. That's a Campbell Graduate Engineering Center, and a bunch of industrial buildings. And so we have, for instance, BMW's IT Research Center for the globe is here. We have a major process development center for Koyo Bearings, which is a group within the JTEC Corporation. And we have about 20 other partners that may not take complete facilities, but we built using the EDA funds from the government. We've built space for companies to come in. And so we have 20 plus additional companies that are here, all engineering related companies and all around the automotive industry, maybe not necessarily directly automotive people. And so this campus is poised for growth. So we have these additional neighborhoods and we have additional areas that and additional interest from other companies. And so we can grow over the next decades and become something that, very powerful, I think, in the research community. And it's about academia and industry working together. I think you could see on that picture there the cobblestone streets. So there's a lot of walking space here, and the idea is that academics and industry people can walk across the street and meet out in the atrium area or outside in the seating area and sit and start to have conversations that could turn into something.
And that is super important. And we're gonna jump into research. So we're gonna start talking about the research elements. I do have a question for you.
Sure.
From Jean from France. He's asking, how important is supply chain software in your industry, and what are the main pain points you face with supply chain? I want to say something first. For some reason, if you set your systems on private, I see only LinkedIn user throughout the system. But if you post your questions, like I can see your names on the actual LinkedIn. So don't worry. So Jean, this is your question. Laine, tell us a little bit about supply chain software.
Yeah. So supply chain in general is critical to the automotive industry, not just from the logistics side, where cars need to ship and be serving different markets, because different companies have different strategies for that. Some companies are build it where you sell it. Other companies are let's take the SUV expertise that we have, and we're going to build all our SUVs in one plant, and those are going to go out to the world. But on the input side, the supplier has become a critical partner for the OEM. When Henry Ford started making cars in Dearborn 100 years ago, he got nuts and bolts, but everybody was right there in the factory putting everything together. The work content has transitioned slowly but steadily, and actually more rapidly in the past 20 years, from a in-house to an outsourced effort. So the value addition from the supply chain is now upwards 60 to 80% of the car. So now you have suppliers that don't just know how to make a bolt. Now they know how to make a module. So they might make a steering module, and then the whole thing comes in, and the OEM has really transitioned to a clicker together of modules, and final system level validation of the functionality. So that supply chain is really important. As far as software, I'm not so familiar with all the different software that's used for supply chains, but I do know that there are a number of examples, such as an axle manufacturer here in Spartanburg, South Carolina. The axle manufacturer doesn't know what they're going to make 8 hours before it has to be on the floor at the OEM. So they get their orders, 8 hours ahead of time. They have an idea, right? They know what different kinds of models they can make, but the mix that they're going to have to put together, the options they're going to have to include, and the sequence in which they're going to have to build them is only available to them 8 hours ahead of time. That is only possible because of the big Industry 4.0 or digital manufacturing network that we have now. So that, from that sense, building in sequence or building to order and building just in time is key.
This is awesome. One day I'm going to be doing this question that John asked is very spot on for anything, for technically anything in the world of manufacturing. Whatever manufacturing domain we talk about, what you just talked about, Laine, is the fact that someone can ask for something, and in 8 hours the manufacturing needs to be initiated. How many triggers?
No, in 8 hours the manufacturing has to be completed. So and it has to be on the truck and delivered in 8 hours. It's amazing how it happens. But you're right, and the flow of information and the format of information. Can you imagine that you're a company and you have to deal with 200 different suppliers, and each one of them speaks a different language or has different format for their data? How do we address that? That's some research that's going on right now.
I completely agree with you. So let's start talking about manufacturing process estimation and control. So we have three things in here. You want to talk to us a little bit more about them?
Sure. So this is what I started my research on, and it came from my days in the bearing factory and my days in the automated assembly factory for automotive systems, where all the machines were always set up for the worst case. We're like, we make rings in the bearing factory, and they might be this big, but because of process variation, they might be this big. And so all the machines were set up, well, let's set them up for the biggest one, because if we set them up for the small one and a big one gets in there, you got a big crash, and then you got problems. And that always rubbed me the wrong way. I said, well, why can't I check each ring as it's going into the machine? Or even better, have the machine before say, oh, I finished the ring, it varied by this much, it acted this way, watch out, and pass that on to the next machine. Couldn't we be so much more efficient and do that in so much more an intelligent way? And so this idea of estimation and estimating sort of properties about a ring or any products that you put through from the manufacturing parameters. So if I go in and I grind a piece of metal, that grinding process is going to behave differently depending on how the material is acting. So I've heard, even anecdotally, since I started here, we'll talk with some manufacturers and they say, oh yeah, we nominally we're along here, but if I go to a different supplier or I go to a different batch, that can change by up to 10%. 10% is huge in manufacturing.
1% is huge.
Yeah. So that started this whole venture down estimation and control. I started in machining because that had been the area that I had been working and doing just that, cutting a part, using the information that was generated during that cutting and passing that information to the next part, and then finishing it. And then you finish the part and you do it, check it functionally, and then you feed that functional feedback. Hey, this didn't work exactly like I wanted it to, and relating that to some of the manufacturing parameters and sort of feeding that back and making modifications to the process. So that's what we do now, but we do it in joining processes, we do it in forming processes, and now we're doing it in assembly processes with people in the loop. So I'll talk a little bit about that.
That's very exciting, the integration of the human aspect in it. What is the NSF NRT Thinker, the education in?
Yeah, so that doesn't necessarily quite fall under process estimation and control, because that really encompasses people. So this is a 5-year program that was funded with $3 million from National Science Foundation, where we propose to educate graduate students in a new and different way. And the topic is around people and digital technologies getting along better together in a manufacturing environment. We have this thing called Industry 4.0, or the Industrial Internet of Things, which is on the rise now and evolving, where machines and software systems and robots are all exchanging information and talking to one another. Very soon, we'll see AI as part of that, artificial intelligence, making decisions really quickly. And the person in that loop, maybe the person that's turning the wrench, maybe the person that's programming the robot, maybe the person that's managing the operation, might start to think, well, where do I fit in with all of this? And I think that's a valid question. And so that's what we address in the Thinker program. Thinker is technology, human, integrated knowledge, education, and research. And so we're looking at how technology and humans get along, technology being highly repeatable, highly automated, maybe highly dedicated, and humans being a little bit more subjective, a little bit more adaptive, and a little bit more creative. And so these things are sort of a dichotomy, and how do you bring those together in a digital environment? So we do this vehicle assembly center that I'm in is the playground for the Thinker program, and it's actually a graduate program, but we're here in a technical college building. So this is Greenville Technical College, and Clemson got space inside Greenville Technical College, and so we carry out these projects with these project teams, and we have the graduate students working together with undergraduates from Clemson and working together with Greenville Tech students and solving a problem as a team. Weird. That kind of sounds like the real world. You get out in a company or in a factory, and you're working with people that are not just a bunch of graduate, students, not just a bunch of PhDs sitting around solving problems in the factory. You have to work together in teams. So students take courses in teamwork and collaboration. They take self-evaluation, so they understand sort of what their strengths and weaknesses are, and they share that with one another. And then we work together on a project, on a vehicle-based project or on a robotic-based project together as a team.
This is awesome. If anyone has any questions, please go ahead and shoot them. So let's talk a little bit more about information generation for manufacturing.
Yeah. So that's the way that we take manufacturing information and feed it forward to the next process, or alert the human, or alert the person in the process. So where does information come from? We need to make clear that we have data, which is numbers that are coming from sensors, or is not measured at all. We might have data like where my hand is in space, and maybe I can measure that, and maybe I can't. And then we have information. So we have data that might be like force in a machine tool, right? How much force can I measure? That's just a number. But if I can use models to relate that force to, for example, tool wear or to material behavior, then I can start generating some information about how that force can be modeled as a function of some of these other pieces of information that I might be interested in, and use that kind of information. And when we say sensor fusion, that information could come from multiple locations. So I might measure machining force, but I also might measure the temperature, and I also might listen and measure the sound. And each one of those streams provides information, but together those streams provide even more information. So we can look between the streams of data, and the way that those things vary with one another can also provide additional information. That's the basis of sensor fusion.
I mean, this is the holy grail, right? Taking data, transforming it to information, eventually generating knowledge, so that you can actually take action using this data, and not only having a big block of data. Is this your research team in here?
Yeah, so that's the group. A couple of them have graduated. We lost a guy on the left. He graduated, and he's up at the Penn State Applied Research Lab now.
Isn't it hard when you work with someone 4 or 5? I mean, this is what we are doing. But you develop those relationships, and suddenly they go, and it's like sending your kids away.
That's exactly what it is. I mean, these folks, they come in. A lot of times they have no idea what research is. I was the same way. I came in, I could do engineering, that was great, and I had to get recalibrated on research, which is knowledge generation rather than stuff generation. And so I work with every one of these folks to sort of help them turn the corner, understand that, pick a topic area and really move forward with it and go. And it is such a joy to see, when it's pushing them out of the nest, right? So when they could start flying on their own, and that's about the time they graduate, and that's the biggest heartache of the whole job. The hardest thing is finding these folks in the first place, because this is not a place for the faint-hearted. And the second thing is watching them go. We got another one here. He's just got a job at Cummins Engine. He's doing a fantastic job now, and he's getting ready to go off to Cummins, and so we've got to say, all right, next. So it's a killer.
But this is why we love what we do, and this is why we do what we do. It's because
it's very positively reinforcing, and we're setting these folks up for a glorious future. So they're going to do really well when they come out of here.
It changes my day when I receive out of nowhere a message from a student that stopped working with me 8-9 years ago, and he's like, I remembered you today because you taught me this, and I'm like, all right, I'm done for the day. Yeah.
I like the messages was like, hey, Dr. Mears, I just got made the head of the entire quality organization within this major company. I'm like, wow. That's the kind of cool stuff that you hope you were at least had a hand in that you were a little part of that.
That's awesome. So we didn't talk a little. We talked. I mean, you talked a little bit about communication edge and making sure that we're getting information from.
Well, yeah, and that's a good point. We can also mention there that a lot of companies and a lot of folks make the mistake of, oh, these sensors are so cheap now. I'm going to put these sensors everywhere. I'm going to have so much information, and that's wrong. You're going to have so much data. And I go into companies and I see this all the time. They're like, here's our data. And, they have 10 terabytes of data that they've been collecting over the past 3 years.
And it makes sense.
And what does that mean? I don't know. We just streamed it to disk and we got it, but we got it, but you're not using it. And that's what this is all about, is what information, you go backwards, right? What information do I need? Therefore, what data do I need? What's the minimum amount of data? Can I use this sensor fusion to just get the little amount of data that I need and draw a lot of information out of that, and be a little bit more efficient about it, be a little more smart about it.
So I have a question for you relevant to computing power needed to achieve data analysis in the cloud. And for example, are you considering using the new 5G network to access data in the cloud?
Yes, so we're building a 5G network here on the ICAR campus. It's going to be more for automated driving, and which is the other major area of study in automotive engineering right now. But wireless data is important. So how much data you can get through to something, but having just being aware of, I can have little devices like this that go around with the objects that I'm tracking. It could be this skid that's going back and forth behind me. It could be a vehicle. It could be something. There's a lot of computing power on one of these things, and this is a transmitter as well, but I can do a lot of computing directly on here. I can also use the wireless or the Bluetooth, stream that to a local system, and I can get a little bit more computing power there, and I can get a little bit more sophisticated information. It takes a little bit longer, right? I can do things like we do wearables with embedded systems like this, and I can take that and I can, do an operation and immediately get a feedback. Hey, you did that right, or you did that wrong. Okay, well, I can get a little bit more information from a PC that sits line side or a PLC that sits line side. It takes a little bit longer, and I can get even more information from my fog nodes, which are the edge of the cloud, and I can get a little bit more information if I upload stuff to an Azure system or an AWS system, Amazon Web Service system, and do a little bit more processing. And I can get even more information if I put it on a large scale high performance computing cluster. But the more information that you want, the longer it takes, the more computing power it costs. So it has to be worth it. Those are decisions that we have to make in manufacturing because it's a cost driven industry.
Do you agree with my following statement? And I hope you do, because if not, one of my research is in trouble. That although having computing on the fly is, it is important. In some situations you want that, but also having communication ability to transmit things and then have something else compute and then send you back, like almost, today's technology is not there at this point to do it like everything on the fly as we're talking about it, but almost in a certain rapid manner. I feel like this is a closer thing that we can reach versus something that computes on its own recipient.
Yeah. I think about these things in terms of time or frequency, where you can have very rapid sort of closed loop of something like a position control system, right? You might be in kilohertz on a position control system. And then you imagine something like a quality control system. I might have an in-process quality. If I'm grinding something, I might be measuring it as I'm grinding it and adjusting the cycle as I'm going along. Post-processing, where I might make a part and then take it out and measure it, and then go back and make some adjustments automatically. Or making a bunch of parts and taking them off to a quality lab and testing them for 8 hours, and then coming back and making some sort of summative changes. Those all have merits, and they all have drawbacks. And so a good balance of a quality strategy is just a good balance, like an information strategy, that you have to live within these shells of time or frequency and the quality of information that you can get out.
So you might not believe what I'm going to say, but we're 40 minutes into the...
What?
Yes, we are 40 minutes into the discussion.
Okay.
So, which is awesome. This is the goal from the get-go, is people send us questions, we have a discussion, and this is really the goal from all of this. There is no, we have to do certain thing.
Yeah.
So this chart shows a little bit like this is where you are right now, obviously the full assembly vehicle. What is it about? Like, is it like a simulation of a assembly line?
Yes, that's exactly what it is. So we did work with BMW. We've done work with other automotive OEMs. My group is very applied, and so we build prototypes of things that we want to go try on the. We use our research to drive the design of prototypes, and then we want to go try those prototypes out. BMW's been a fantastic partner that we've partnered with them for over 10 years. But there ain't no shutting the line down at BMW. So if you want to test out a prototype, they might say, oh, okay, yeah, we could take you from 3 a.m. to 3:10 a.m. on Wednesday, and you can come in here and try your thing, but make sure it's all out of there by 3:10 because we have to start everything back up. And so that didn't sit right. Particularly, we can't go in and put in a prototype and have it break something and shut the line down. That would be a big no-no. We're guests.
I mean, we would be losing money.
and money from a very profitable company that sells a lot of cars. So we said, well, why don't we just build our own assembly line and we can test our things out here. And as a matter of fact, we have a lot more control about what's going on, and we have opportunity to fail and learn, like you said, Ramy, which is very, very important. So you can see it better in the picture here, actually, than where I am. But we have a vehicle that can go by. We can adjust the speed of that line. We can raise and lower that vehicle. This is actually a production skid from a BMW factory that we retrofitted to run on these rails on the floor. And then it's 3 stations. So we built this little static platform next to it. The static platform has a very high payload, so we can have people walking up there. We also have robots up there. We've tested mobile robots up on there, so robots that can go get tools or parts and bring them to the person. This is something you don't see very much in an assembly factory, but it's an idea that we can try out here. And it doesn't have to be fully developed, and it doesn't have to be economically viable. It's just, let's try it as a proof of concept and see what kind of thoughts that leads us to.
We have a question, and it's a very interesting one, because very often people think that since something is working, I mean, especially us, don't mess it up. So Banu Prakash is asking, I always wonder in established companies, and he cites BMW, since most systems in the assembly are already present, is there scope for fresh graduates to involve in research? What are some of the topics that are hot when it comes to changing assembly?
Yeah, good. That's a bunch of questions altogether, and all very important topics. So first, I can say that if you're talking about manufacturing research, or even if you're talking about product research in the automotive industry, you have to be aware of the company. There are companies like BMW, for instance, that just does manufacturing here. So they do some manufacturing research here. But if you want to change the design of a vehicle, you have to go back to Germany in order to do that. That's different than a Honda Marysville, for instance. Marysville is a factory. Across the street is Raymond, where they do all of the vehicle design, and everything is completely enclosed there. So you have an opportunity, maybe a much closer link, at least in time, of the manufacturing and the design operations. You say they work in a preset manner, and I take that to mean, and it sounded like Ramy took that to mean, it's working, so leave it alone. Don't make it better because you might break it. This is a really, really big problem in manufacturing. It's a really, really big problem in vehicle design. This is the reason we have vehicles that are still made out of steel, because nobody's taken a step back and said, let's just erase everything and start over brand new. And what would a vehicle, knowing what we know today, not knowing what we know and taking the existing vehicle and trying to make it a little bit better, but knowing what we know today, if I were to reinvent vehicle, what would that look like? Would it be a steel frame and maybe some aluminum panels, stuck on the outside? I highly doubt it. We can look at a manufacturing system the same way.
Can I say no?
Yes, you can. You would be right. So we can look at a manufacturing system the same way. If I were inventing a manufacturing system, let's invent them together. Let's invent a vehicle and a manufacturing system, since they're highly coupled. Would I really be investing in $1 million stamping dies? Is that the best way to spend my money, or are there other ways to do that might be make a little more sense and be a little more flexible, be a little more agile once people decide what they like and what they don't like? So there is a lot of opportunity for research, and companies that have their mind open to these types of things. You can't take a factory and throw away billions of dollars of capital. I understand that, but you can bring some new ideas in there and some very radical and highly variable ideas, and make a difference. So let me leave it at that.
I agree with you. Laine, let's talk a little bit about the human augmentation research. I mean, in line with what Banu was just asking on, like new things that can be worked on. Talk to us a little bit about these smart sensing gloves and where are they used in assembly?
Yeah, this picture is actually an earlier prototype of one that we've built. And this actually is in conjunction with manufacturing research. This is with BMW, with manufacturing research in Germany. And now we have a glove that can listen for things. So we have a glove that we've clicked things together, and it listens for that click, and it uses modeling to decide if that was a good click or a questionable click. We have force sensors that in that picture, they're not hooked up, but in our current glove, they're integrated in. And so we're doing force sensing of the fingers and hands, right? What a great machine, right? The hand, I can't build a robot that does this, but I can get data off of this wonderful machine, and I can do something about that. And that's the idea behind this. We've even developed gloves that have cameras built into the glove, so I can reach into a body cavity that I can't see on a car and can't see, and get some visual feedback, maybe with an AR device or with an external screen, so I can see what I'm doing in an area that's typically blind. And it improves quality, improves productivity,
improves ergonomics as well. I mean,
and it can be used for ergonomics. So ergonomics is typically done using external measurements on a sampling basis. Here, I might put a force glove in, put force sensors in a glove, and I can have somebody actually take continuous ergonomic data and flag when they have a problem.
I think this would be an important goal for safety, especially.
Yeah, it's for safety, and this is also a driving force with this was providing data to the Internet of Things and getting information back in different ways from the Internet of Things. Do I have sound? Do I have lights? Do I have pictures? Do I have, and other things, right? Electric shocks.
So
That's a joke. That's a joke.
Yeah, I know. I hope. So talking about material joining research, talk to us a little bit more about that.
Yeah, so I'll be brief because I realize that time is going. This is, companies have now started breaking the cycle of let's just keep making cars out of steel, because that's the way we've always done it. Steel's a great material, right? It's formable, it's really strong, it's really tough. It is dense, so there's weight problems with that, and weight is almost linearly correlated with fuel economy. So lighter vehicles use less energy, and we would love to do that everywhere, but we're not going to triple the cost of a vehicle. So there's a balance that you walk there between manufacturability and cost. And companies are doing this now. So we see, like 2015 was the Ford F-150 all aluminum body that came out. Slightly improved fuel economy, but greatly improved towing capacity and specifications. But you can't
There's always a but. Go ahead.
You can't just take steel off and make aluminum parts and put them on and off you go. So you have to deal with, okay, well, before we were spot welding these things with electricity, aluminum and steel behave very differently in spot welding, so I can't do a spot weld practically between steel and aluminum. So what do I do? That's been a large part of our research. We started with an OEM who will remain unnamed, that was developing a very high-end car that had a lot of aluminum on it, and they were exploring 6 different joining technologies. So we did a lot of study of a lot of different joining technologies, and these are some of the ones that rise to the top now. So in the left lower diagram, this is flow drill screwing. It's widely used commercially now for doing aluminum joining, one-sided, which is great. and aluminum mild steel joining. If the steel gets stronger, so high strength steel is another lightweighting material. It's a lot heavier. It's a lot denser, but it can be a lot thinner, so it can actually become lightweight. Friction element welding is a kind of an entrapment of a aluminum sheet and then a friction weld to a steel sheet below. And we've done some cool stuff. We've put screws through ultra high strength steel, which you can't do. So I love doing things you can't do. so that's some of our research and some of the challenges that we do here.
So just for my own curiosity, friction element welding, mm-hmm. I didn't understand that. And like, this picture is for it. So talk to me a little bit more.
Sure. Oh yeah. So the element is the screw, but there are no threads. But it's the dark part on top, and it's spun and pressed down into the aluminum.
Is this it?
That's the element. That's correct. So it's a steel element that's rotated at 6,000 to 8,000 RPM and pressed down at 6 to 8 kilonewtons. And it friction drills through the aluminum. It heats the aluminum up enough where the aluminum just sort of sloops out of the way. That's an engineering term, right? and then it comes in contact between steel and steel, right. And then a lot of heat is generated there, and you actually get into a solid state flow of material, commingling of material, and then it solidifies. And now you have kind of a capture element of the aluminum sheet to the steel.
I got it. And for terms, you're allowed to create any term that you want as an engineer.
Okay, great. Oh, wow. I'll be careful.
So let's talk a little bit about the NSF Thinker. You did mention it a little bit before.
Right. So I can go in just to what the students get to engage in. So they don't just take classes. So it's much more comprehensive than that. So students do this collaboration and teamwork and self-evaluation. They also go through a host of professional development activities. That's not a resume review. That's sort of putting them in with industrial partners, mentoring with industrial partners, and saying that what are the keys to success that you might not get from a traditional academic kind of program. We bring in professionals in teamwork and team evaluation, in personal introspection evaluation, and a number of tools. So I'm sure you're familiar with some of those. And then the students also get to present to university leadership every year. So they take their research that they're doing or their project that they worked on in the project-based class here in the Assembly Center, and they present to the Vice President of Research and his team each May.
How important is this? I mean, I stress that so much for our students, because this is these kind of experiences. So we have the McNair Junior Fellows program here at USC, and these are the kind of programs that like take someone and shake them into an environment that is the actual real environment. Like it's really beyond the classroom teaching.
Oh, it's critical. I mean, you have to be first of all, you can't just sit in a classroom and do problems because you won't understand the context. All right, why am I working on this? I've heard from a number of students, when we're working on research, oh, that's why we learned about, Bode plots in frequency response class. Yeah, but you should have been told that when you were learning about it. You should have understood the context. So being able to do that, and then the ever popular, hey, Dr. Mears, you didn't give us enough information to solve the problem. Now you're starting to understand. Now you're getting into what's called the
reality of things. I mean, you never have full information and then the disruption that comes along the way. I mean, like even if you have something defined, you're gonna have a disruption that's gonna change the definition.
Oh, of course, right, exactly. So what do you do now? So what do you do when the designers throw aluminum car at you instead of a steel car? Hey, our spot welders don't work anymore. Do something about that, right? So how are you going to approach those kinds of problems? What are your assumptions going to be? What kind of research background are you going to look at? What kind of models are you going to have to make? And what kind of decisions are you going to have to make? And what's the uncertainty associated with those?
This is awesome. So Laine, I know we've planned a tour, but we are a couple of minutes away from the clock.
Yeah, I can show you. I can show you a couple of things. I hope.
All right, let's see them.
Like my phone might have gone to sleep. I'm going to.
I think you got a phone call in the middle of that.
Maybe that was it. Somebody's saying, "I see you online." Here, let's see if this works. Allow. All right, I'll. There goes the camera. Okay. So how does that look? Can I?
You're not on the system anymore. Like somebody kicked you out from the system.
Oh, sorry.
On your phone. You have to click back to join. And no worries, take your time. There is okay, here it's coming.
All right, I'm backstage.
Loading. Your guests will need to connect to their cam mic. Okay, you went out again.
Now I'm entering the studio.
All right, as soon as it pops up to me, I will share it. And if not, I mean, okay, here something's coming up.
Yeah, I can show you a couple of quick things. That's Ramy.
All right, let's see. I'm gonna add you to the stream to see. So your camera is not enabled on the other. Oh, I see you now twice.
Yeah. Good.
Okay, I'm gonna remove the main one. Will you still be able to hear me if I remove the main one?
Hopefully. If not, I'll just talk.
So the other camera you have is still like it's not moving.
Yeah, it looks like it's trying. Nope. Okay. Maybe we'll have to skip that one.
Yeah, I mean, very honestly, in a couple of minutes, it's going to be very, very challenging to do that.
Yeah.
But I think
I can show you around. How about this? You know,
let's do that. Yes, I was wanting to ask you if you want to carry your laptop around.
See, I don't mind to do that. I'll put up a little bit high. You can see on the wall behind me, we talk about technology readiness levels. So that's how research translates into practice in the factory. That's a very important point to understand where you are with that.
So
let's go and see Ethan here.
The viewers on my LinkedIn are very familiar with this. Hey, Ethan.
So here's Ethan. He's a mechanical engineering student that's working on a master's and PhD. So he just got back from 6 months in Munich working with robotics people of BMW, and now he's bringing some of his information back and doing some testing with us. And so this is where we bring robotics to the manufacturing line and take a look at that, how those things can kind of interact with one another.
So what is it that's simulating? The fact that the car is coming back. So it's coming back to another station?
Yeah, that's just sort of resets. So the car flows back to the starting point, and then it will move forward and go like station 1, station 2, station 3. And then for each of these stations, we have it's not open, but we have PLC box. So we have computers inside each one of these, which are industrial computers, and they line up with tools, any kind of tooling that's used in a factory, any kind of sensing that's used in a factory. We can replicate that here. You can see sort of up behind me the speaker. So we have a surround sound speaker system as well, and we've gone in with some very nice high fidelity microphones and recorded factory sounds that we can come in here and we can turn those factory sounds up and down and see what kind of effect that has on people that are working in the factory.
Oh, that is so.
Things get loud, and when things get quiet, both of those can be detrimental, actually. And we're working on lighting. So right now we have kind of standard industrial lighting. We'll put in variable lighting here as well.
This is an economics playground. I mean,
this is it's my warehouse. So we have
wow, that's awesome.
And one of these will be, so here's our space now.
Laine,
the next thing
I have a question for you. I have a question for you.
Sure.
Now, do you on Saturday go to play in your lab? Just like it's not working day. I'm like, hey, I'm gonna go and play today.
I take a break, but I actually have been shedding some of my more ancillary activities so I can spend more time in here, spend more time with the folks. The more time we spend together, the more ideas start flowing, and that's really where the magic happens, I think.
I agree with you, Laine. We've come to time with our little chat for today. This has been. I want to ask everyone on the chat to press the clap button. I like this clap. So that this is our virtual way to thank you, Laine,
Okay, all right.
for your time today.
That's really meaningful.
It was really, really nice. I really enjoyed it myself, and I'm looking forward to the continued professional and personal relationship. Thank you so much.
Yeah, me too, Ramy. Thank you for the opportunity, and again, thanks for the time that you put into doing stuff like this. It's very important for the research community, important for the engineering community, and important just for people to understand these issues. They're really pertinent right now to the economy and to prosperity.
Thank you so much, Laine. And you know what makes me really, really happy is the people that we reach through these initiatives were like, I mean, from India to all over the world. This is nice. I mean, this is really cross-cultural community outreach, and I love to do that. So thank you so much.
I'm jealous. I might join you. Maybe I'll become your partner.
Hey, let's do that.
All right.
Laine, thank you so much.
Okay.
And everyone on neXt. So this was the unofficial ending of this season. We've had 11, 12 live sessions. There's still one more live before I take off for my Christmas break from the McNair Center at the University of South Carolina. Laine, looking forward, and have a great rest of the day.
Okay. Thank you, Ramy. Thanks, everybody, for your time.
Bye-bye.
Bye.